Hyperparameter auto-tuning in self-supervised robotic learning. Goals reinforcement learning can achieve multi-goals. Recently, in reinforcement learning with image goals, agent can without a specified engineer reward function to learn different tasks in a self-supervised way with the help of using visual observation and VAE-based goal generator. We learn visual reinforcement learning with image goal as RIG. In RIG, the training progress is separated by sequential epochs. Each and every epoch has an exploration phase, policy update phase, a policy evaluation phase, and a VAE fine-tuning phase. However, it is a challenge to search so many hyperparameters to guarantee the best performance. For example, if we choose limited size of replay buffer, it is possible that the replay buffer is filled. If so, once lower transitions are stored, they will replace previously stored experience, leading to forgotten behaviors from previous steps. If we choose limited number of gradient update steps, the agent will learn suboptimally given the transitions from replay buffer and use a suboptimal policy in next epoch. If the number of exploration steps is insufficient, we will optimize the current policy with only a limited number of collapsed transitions, which may lead to a suboptimal policy too. To reduce the work of hyper-optimizing those hyperparameters is a challenge. We study to learn the number of different goals we have generated for policy learning. We find that VAE's loss function, also called mindless evidence lower bound, having a lower bound relating to the entropy of the training samples. In VAE-based goal generator, the number of different goals for policy updates is related to the entropy of samples. Finally, we can use single hyperparameter C and the value of evidence lower bound to approximate the number of different goals. After know the number of different goals, we can compute the minimum number of size of replay buffer NR, the number of gradient updates N theta, and the number of exploration steps NE. Usage of auto-tune is simplified in algorithm 1. We base on the approximation of the number of different goals to auto-tune 3 hyperparameters online instead of fix them from the beginning. Our experiments are answering the research question below. We first testing on image dataset like MNIST and fashion MNIST. We use the label to select the samples diversity for training the VAE. For the learn selected samples, we change the sample's pixel values to 0. The pixel values change will change the distribution of the sample, which will change the entropy of all the samples directly. When diversity degree of the sample increase, the entropy of sample will increase or vice versa. You can see when the diversity degree of samples increase, the value of minus evidence lower bound increase or vice versa. Then we can use single fixed hyperparameter C and the value of evidence lower bound to approximate the number of different goals. We tune the number of replay buffer with max path length times the number of different goals. You can see auto-tune can choose sufficient number of replay buffer size to have same performance compared with use redundancy number, but take less computer resource. We tune the number of gradient updates with the number of different goals directly. We can see AutoTune can choose sufficient number of policy gradient updates to have same performance compared with use redundancy setup, but take least total gradient update steps. We also tune the number of exploration steps with the number of different goals directly. You can see AutoTune can choose sufficient number of exploration steps to have same performance compared with use fixed redundancy number, but take least total exploration step too. We also testing auto-tuning those hyperparameters in real robot. We find that auto-tune can adjust the hyperparameters without any hand tune rod, which leading to learning faster than use fixed hyperparameters after the rod space is large. Additionally, we test the policy behavior with all possible goals, not only the task-related goals in push environment. You can see AutoTune has similar coverage area of the environment compared with redundancy setup. Continually, we develop AutoTune in curriculum change environments. You can see AutoTune has capability to change the hyperparameters because of the evidence urban change, which is responding to the environment's diversity degree change. Finally, we can see AutoTune also useful in multitask setup. Auto-tuning achieves the optimal performance directly in terms of learning efficiency and time consuming. In summary, our work identified that the loss function of VAEs has a lower bound related to the diversity of samples. To avoid suboptimal learning or waste computer resource, we propose a methodology that auto-tunes 3 hyperparameters. We experimentally validate our approach on diverse domains, and we additionally report competitive performance in more general settings. Thank you.